Testing A, check. So, do you like this view? Yeah. I think you like this view.
Thank you very much, Hakan, for your kind introduction. And thank you very much for coming today here and also online. It's my great pleasure to talk about my experience and my research here at KAUST. So again, the title of the talk is Ultra-Wide Bandgap Semiconductor for Future of the Moore's Law. So first of all, I would like to have a quick introduction to myself, especially my experience here at KAUST. Just a quick overview again. I got my PhD, master and bachelor degrees from Georgia Tech, Lehigh University, and HUST respectively. And then after receiving degree from Georgia Tech, I was fortunate enough to get an offer from KAUST and then joined KAUST as an assistant professor in January 2016. And in 2017, at that time, the university was thinking about building applied physics program. So I was part of the founding task force to create the applied physics program, and therefore I'm secondary affiliated with the applied physics and PSC as well. And I got promoted in July 2021 as an associate professor. So here at KAUST, I have been fortunate enough to get multiple opportunities to provide service to the university. I was the chair of the founding task force, and then the member of a working group of the Technology, Innovation, and Entrepreneurship Program. We just graduated the first cohort in December last year, and now the second cohort is starting here at KAUST. I was a member of the founding task force and later became associate director of the KAUST International Innovation Hub from December 2022 to today. Thank you, Hatan, for coming. And then I was also a task force member and the chair of the operations subcommittee of the Semiconductor Initiative. And one of the major events that we organized as part of the Semiconductor Initiative is the Future of Semiconductor Forum, which was attended by well over 1,000 people. And then we also got a lot of sponsorship from the industry and then a high-level official coming here from the Saudi government. And then since 2016, I have been also a founding member of the Photonics Summer Camp, which I'm serving as a chair this year, and also a founding member of the Microelectronics Winter Camp. So through those camps, we have brought hundreds of excellent students from all over the world, many of whom actually became the full-time master and PhD student on campus. And also since 2016, I have been helping with the Chinese student recruitment, especially from a couple of top universities like UESCC. And I believe that the UESCC today is the largest PhD student pipeline on campus for PhD study here at KAUST. And also working with Marcom previously and now GBC to create and then operate the social media in China as well. And also in ECE, I've been lucky enough to serve on different committees like admission, faculty research committee, curriculum, and outreach committees. And also I've been the member of the steering committee of the nanofabrication collab and then the imaging and characterization collab. So in terms of research and teaching interests, I've been my research interest in the related to material physics, device, and IC research of ultra-wide bandgap semiconductors. And therefore, I have been teaching several courses at 200 and 300 levels related to semiconductor. So on average, I've been teaching about 2 courses per academic year since I came to KAUST. And then so far, I have graduated 15 PhD students. I have mentored over 40 master and over 60 visiting students and scholars. I have also advised 8 postdocs, and I have been part of over 90 PhD and master theses and proposal committees. So in terms of scholarly outputs, I have published about 190 journal papers since I joined KAUST, and 76% of that are led by my group. I have published about 250 conference publications and presentations since I joined KAUST, and I have also given about 140 plenary keynote / invited talks and seminars in research organizations, conferences, and companies. So in addition, I have received different awards. Some of the awards are from the top conferences in our field, some are from different associations. So in addition to those, I've served as on the editorial board of 3 journals, Photonic Research, Journal of Semiconductors, and also Advanced Electronic Materials. I've also been on different committees of about 45 different conferences, most of which are leading conferences in our area. Okay, let's switch gear and talk about a little bit technical stuff. So this slide here shows basically how the density of transistor has increased over the years. And this was largely in line with a prediction that Gordon Moore, who is the co-founder of Intel, made about 6 decades ago. And in the last 6 decades, the transistor of density has increased, has doubled every 2 to 3 years. For example, if you look at between 1997 to today, the density of transistor has increased by 5 orders of magnitude, which is astonishing, actually, improvement in the transistor density. And however, in the last 10 years or so, ever since like after 14 nanometer, 10 nanometer till today, 2 nanometer, the Moore's law has slowed down greatly, right? And because it actually has hit 2 walls. One is quantum mechanics, and the other one is processing technology. And some of the leaders in the area, for example, like the founder and CEO, Jensen Huang, even claim that the Moore's law is actually dead. And basically, you have to switch to his GPU and other techniques to continue the improvement in computing technologies. However, obviously, as the birthplace of Moore's law, Intel actually strongly rebuted that. And they say that actually the Moore's law is still well and alive. But regardless, I believe that it is obvious that the Moore's law has slowed down greatly compared to before. And I think this is a historic opportunity for ultra-wide bandgap semiconductors. So let me explain why. So this is an oak tree, and it's a common plant in the northern hemisphere. I would like to use this oak tree to represent the whole semiconductor industry and ecosystem. So if we use, use the invention of the transistor in December 1947 as the sprouting moment of the oak tree, and then in the last 6 decades or so, the Moore's law has driven the growth of this oak tree to have a super strong and robust trunk, right? And recently, the industry group predicts that the global chip sales will actually hit $1 trillion for the first time this year. And also, if you look at the top 30 most valuable companies in the world today, 8 of them are semiconductor company. But in addition to that, technology companies like Apple, Meta, Tesla, Alibaba, and others are actively developing their own chips for the different applications as well. So as I mentioned, the Moore's law has slowed down greatly, right? So it's no longer viable to just continue to grow the trunk. This oak tree has to seek alternative path, which is to grow new branches. So there are 3 major branches related to the growth of the semiconductor oak tree. One is more, second is more than more, the third one is beyond more. So let me explain them one by one. About more is about how do we continue to grow the transistor density, right, beyond what we have today. So the purpose is to increase the computing power and also improve the efficiency. You can realize that by different means, for example, like extreme UV and FinFET, gate-all-around, high-K, dielectric stacking technology. Some of the terms you may have heard from different news, right? And the about more than more is more about functionality. Okay, so in addition to just use brute force to increase the transistor density, can we add different functionality into the whole electronics plus / photonic system so that we can further improve the efficiency and computing power, right? So that's where people introduce, for example, optical interconnect, power via, the use of different analog devices into the whole system, the use of 3D packaging based on chiplet technologies. And beyond more is another one. Beyond more is how do we propose new paradigm so that we can revolutionize the computing power. For example, we may have heard quantum computing, right? Neuromorphic computing. Those are different computing architecture, and ambipolar CMOS computing as well, which I'm going to talk about later. Another one is that how do we move the computing system, electronic system beyond the Earth surface that we are living in today, right? Can we move the computing to the space, right? This is something that, for example, Elon Musk has talked about a lot recently, is that how do we do AI in space? So the computing in extreme environment is also part of the new paradigm as well. So obviously, a normal oak tree will bear acorns, right? So here, this for a semiconductor oak tree, those acorns are different important areas of the human society, including AI, mobility, entertainment, water, food, health, so on and so forth. So to grow a nice plant, you know that the soil is the key, right? And so if you look at how do we grow, from the trunk into different branches, the question is that how can we identify the right semiconductor materials to be part of the soil to continue to grow this oak tree? So next, I would like to introduce you several major waves of world-changing semiconductors. So there have been 4 waves of world-changing inorganic semiconductors. The first one started with silicon and germanium, right? Bratton, Balting, and Shockley invented the first point contact germanium-based transistor in Bell Lab in December 1947. So that was almost 80 years ago. And this was also regarded as the greatest invention of the 20th century. And since then, there have been a lot of breakthroughs related to silicon and germanium. There have been 3 Nobel Prizes related to that: transistor, integrated circuit, and CCD. Nowadays, most of the computing, memory, imaging are all based on silicon and silicon germanium, and also a lot of the legendary power systems are based on silicon. And in addition, the prevailing photovoltaic system on the Earth's surface are also based on silicon. The second wave is the 3-5 semiconductor, right? So they have a slightly larger band gap compared to silicon and germanium. However, the big difference lies in that it has direct band gap. So this means that they can be made into very efficient lasers, LEDs, and photodetectors, and they have become the backbone of global internet today. In addition, the electrons and holes can move very fast in those 3-5 semiconductor, right? So, and therefore, like today, the world's fastest electronic devices are also based on 3-5 semiconductors. And there have been 3 Nobel Prizes related to 3-5 semiconductors, 2 quantum Hall effect, and 1 heterojunction. The third wave is the wide bandgap semiconductors. represented by gallium nitride and silicon carbide. The research of wide bandgap started in 1968 when researchers studied the first epitaxy of gallium nitride. Right? And gallium nitride has a much larger bandgap compared to 3-5 semiconductor. And actually, that bandgap moved it right into the visible range. And because also gallium nitride has direct bandgap, so researchers can make it into very efficient blue LEDs. And nowadays, we are sitting in this room, and most of the lighting and also this display are based on blue LEDs. And as a result, the inventors of blue LED received the Nobel Prize in Physics in 2014, and one of whom, Shuji Nakamura, have visited KAUST multiple times. So in addition to revolutionizing the lighting and display, wide bandgap semiconductor can also be used in two more things. One is power electronics. The other one is RF electronics for communication. For example, nowadays, most of the high-end and mid-end electric vehicles from Tesla, BYD, Lucy Motors, they all use silicon carbide and gallium nitride in the powertrain, right? Which can make their powertrain much lighter and smaller and more efficient. Another one is that most of the 5G towers today are based on gallium nitride and silicon carbide because they have the right power and right frequency to penetrate the building so that we can still have 5G signal in room. And in addition, as we know, there is a conflict going on right now in the Middle East. And it happened to be that most of the modern radar system, right, whether it's land-based or airborne, are all based on gallium nitride and silicon carbide too. So moving above, we have the ultra-wide bandgap semiconductor, right? They are represented by gallium oxide, diamond, aluminum nitride, and cubic boron nitride. Because of the much larger bandgap, they can have a much better power and RF capability compared to even wide bandgap semiconductors. In addition, photonically, because they can now have a much larger bandgap, so people can make photonic devices well into the UV and deep UV regime, right? So that have played a very important role in combating the COVID pandemic because people can use UV LEDs to actually disinfect surfaces, air, and water. In addition, the very large bandgap can act as a host for quantum photonics devices as well. So there are a lot of important applications related to ultra-wide bandgap semiconductor. So I studied, when I studied as a graduate student at Lehigh before, I started to work on gallium nitride. Still today, we are still working on this very important semiconductor. But in addition, my group is actually putting most of the efforts into the ultra-wide bandgap semiconductors. So let's go back to the soil and then the oak tree, right? So if you compare the ultra-wide bandgap semiconductor versus silicon and silicon germanium, they have different pros and cons. But the interesting thing is that because the ultra-wide bandgap semiconductor have excellent and broad device capabilities, and some of which also have excellent scalability and low cost, we can actually pick and choose the ultra-wide bandgap semiconductor and integrate it potentially with silicon and other materials to grow different branches, whether it's more than more, beyond more. So in this talk, I'm going to give a few examples where we utilize the wide bandgap and ultra-wide bandgap semiconductors to grow those branches. For more than more, I'm going to talk about our work on micro LEDs and power devices. And for beyond more, I'm going to talk about our work in terms of developing devices that work in extreme environments. And for more, I'm going to talk about our works related to using stacking technology to improve the transistor density. So let's start from micro LED. So interestingly, if you look at the left, when I prepared this presentation a week ago, I got an email in the morning from Samsung. The title of the email is that 2026 micro RGB, the new standard of color. So after a long time of development, Samsung is finally start to sell the micro LED TVs to normal consumers. And also recently, Microsoft Research have published multiple articles and papers relating to the use of micro LED to supplement and the lasers in the interconnect technology in the data center to improve efficiency and speed, right? So micro LED anyway is a technology that defined with the defined size of LED of less than 50 micrometer. For example, if later if you are interested, you can come to this screen and you can see individual pixel here. So the individual pixel used in the screen here and also in the lighting here have the size of about 500 micrometer, right? So it's a very large size. So when we talk about micro LED, it specifically refers to LED with a size of less than 50 micrometer. So as I mentioned, it's very promising for new display, promising for on-chip communication and free space communication, and also it can realize the ultra high resolution as well. And therefore, micro LED is regarded as one of the ultimate light sources. However, one of the Achilles heels of micro LED is that, once you reduce the size of the LED from, let's say, 1,000 micrometer to hundreds of micrometer down to tens of micrometer, there is a significant reduction in the so-called EQE, which is external content efficiency of the micro LEDs, right? So this will become a severe problem. And then because you don't want to lose efficiency, because the blue LED we use for the lighting today has an efficiency of close to 100%, meaning that most of the electrons and holes we inject from the grid into the LED will become photons. But in this case, you can see that many of the micro LED actually operate at about 10%, right? So you actually will lose a lot of photons into phonons, which are heat. So why is that? So the reason is that, in a normal micro LED fabrication process, people have to use invasive and destructive process called dry etching. Basically, in the dry etching, you use high energy plasma to bombard the surface of the LED wafer to remove those materials to define the pixels, right? So when you do that for a large LED, it's not a problem because most of the active area are far away from the sidewall. But for the micro LED, the active area is very close to the sidewall. The electron and hole can easily diffuse to the sidewall. So this sidewall will create a lot of problems because it has a lattice distortion, element contamination, and surface band bending. So that will trap electrons and hole into phonons instead of photons. So the question is that, is it possible to develop a technology that do not use the dry etching, right? So, so my student and I came up with this idea. So we want to, instead of using dry etching, we want to use a technique which is very cost-effective and straightforward. It's called selective thermal oxidation, right? The selective thermal oxidation is actually very common in silicon CMOS. Almost every single chip we use in our phone and computer today, we have to go through the thermal oxidation. But here we want to leverage this into the micro LED fabrication as well. So this is how we do it. Suppose that we start from like a gallium nitride LED wafer, right? A LED is a PIN junction. So it has P-type active region is where the light is, the photons are generated, and then we have N-type. And then we can cover that first of all, we can cover that by a silicon oxide protection layer. So silicon oxide layer is an excellent blocker to block oxygen from moving into the LED wafer. And then we can put this whole wafer into an ambient furnace, right, where we have plenty of oxygen molecules. And then we can heat it up. Because the silicon oxide protection layer can prevent the oxygen from diffusing into the area below. So it basically defines the pixel size. If we make it into 5 micrometer, the LED will be 5 micrometer. If it's 50 micrometer, LED will be 50 micrometer. However, the area that is not protected by the silicon oxide layer will basically be deactivated because oxygen like to oxidize everything, right? So it will oxidize the gallium nitride into gallium oxide, which does not emit light. So by integrating this process as part of the LED fabrication procedure, we will be able to, fabricate LED wafers, micro LED, without the use of dry etching. So in this study, we have fabricated a micro LED with different dimensions, 50 micrometer, 30 micrometer, and 10 micrometer. And on the right-hand side, we have a very simple display using 10 micrometer micro LED showing the Kaos logo and our lab. So because this technology is very straightforward and cost-effective, we were very honored to be recognized by this award called the Award of Innovation Top 100 from the International Solid State Lighting Association. So this award is only given to up to 10 companies and research organizations each year. And this is my student on the right. And also based on this work, we have also a pen review article related to how to mitigate the sidewall effect for the micro LED. So since this paper was published a little over a year ago, it has been downloaded over 26,000 times. which has become one of the most downloaded papers of this journal, Light Science and Application in 2025. So after discussion of micro LED, I want to move forward to talk about power. So the current conflict in the Middle East actually highlight the importance of the power infrastructure, right? Actually, we are in a lucky place where we still have sufficient power and gasoline. But many countries nowadays already, have to ration out the use of the gasoline and different powers, right? So, and the robustness of the power infrastructure is measured largely by electrification. Okay, meaning what is the share of electricity as part of your final energy consumption? So if you look at China, it's about 30+%. US and Europe is about 20+%. Saudi Arabia today, 17%, right? So we are a little bit still behind from the other industrial peers. So it means that the robustness of the power infrastructure here still need to be improved a lot. So the material, the semiconductors that drive the electrification today are silicon carbide and gallium nitride. So silicon carbide, if you look at the vertical axis, actually handle mostly high power, high voltage application. That include high speed train, power grid, heavy machineries, and so on. But for gallium nitride, it actually handle the low power and low voltage application very, very efficiently. For example, like humanoid robots, drones, small vehicles, consumer electronics, and so on. So this, mobile nature of gallium nitride power devices indicates that we will need ultra low leakage for the gallium nitride devices, especially transistors. So if it does not have a low leakage current or the low, static power loss or the operation power loss, the devices, the final devices like consumer electronics, drones, and humanoid robot and so on, will have to carry a bigger pad of battery, right, which will increase your cost, size, and weight. So this mobile nature is basically, determined that we need to develop very low leakage gallium nitride transistors. So what actually affects the leakage of gallium nitride transistors? So mainly, we have several interfacial defects at the gate that can impact the leakage, where it will increase the leakage. Those are the defect-induced gap states, mix, and metal-induced gap states, mix. And they are largely created because the conventional metal for the gate, nickel and gold, have a direct contact with the gallium nitride, right? But those defects and gap state will act like traps and charges. That will basically deteriorate your gate controllability. So that will increase your off current, right? I off. Basically, this is the leakage. And also will slow down the turning on and off of the transistor, which is called substructure swing. So the question is that can we introduce a novel metal with the so-called van der Waals gap, between the metal and gallium nitride? And also because of that, we can basically minimize these two gap states, right, mix and mix. And it happened to be that, Professor Hussein Al-Sharif is an expert in terms of synthesizing MXene. He has published many papers related to MXene, mostly for energy applications. So one day, my student and I were thinking that, hey, maybe we can use his MXene metal as the gate, because MXene will have a van der Waals gap between the metal and then the gallium nitride, right? So which is actually what has happened. So if you look at the benchmarking of our devices versus the previous report, right? So on the left here is the on-off ratio. Basically is how much, so when the device is on, this is the amount of current divided by the current when the device is off, right? So the higher, the better. The higher, it means that you have lower leakage. So compared to the previous report, our on-off ratio has increased by up to 5 orders of magnitude, right? So what does it mean is that, for the gallium nitride power electronic system, if it's based on our technology, the power consumption is the power loss is only 1 divided by 10 to the 5, right? Compared to the conventional works. And another one is the substructure swing. Basically, you want to have a lower substructure swing so that you can have a faster transistor turn on and off, which can improve your system speed and also improve the efficiency as well. So here, like as compared to the previous work, we also have very low substructure swing, right? So overall, this is the state-of-the-art gallium nitride transistor. And in addition, the breakdown voltage has been improved from about 800 volts to about 1,000 volts. Yeah, so after discussion of more than more, I would like to switch gear a little bit and talk about our work related to beyond more. Okay, in terms of the beyond more, what we want to focus here is that how can we enable electronics beyond the Earth's surface, right? We are living very comfortably right here with plenty of oxygen, no radiation, and a temperature around 25 degrees Celsius. But in order for the human society to continue to evolve, there are different extreme environments that we need to accommodate. We need to develop electronic system for those environments. One of the well-known area is space, right? The space has a very extreme environment. In the deep space, the temperature can go down to about 2.7 Kelvin. And in the solar system alone, the highest temperature of our planet surface is about 500 degrees Celsius, right? So this is pretty extreme. And also for the petrochemical and geothermal, we have to develop, electronic system that can withstand temperature up to 200 and 400 degrees Celsius. Another one is quantum computers. Qubits operate at millikelvin, right? So you have to develop electronic system that can manipulate and control and communicate with qubits at also very, very low temperature. So those are all very low temperature and very extreme environment we are talking about. If you look at silicon, silicon does not survive in those temperatures. If you buy a new phone today, if you look at the user manual, it will advise you only use a phone between 0 and 40 degrees Celsius, because silicon simply does not operate well at very high or very low temperature. So this is where the ultra-wide bandgap semiconductor can come in play. For example, gallium oxide with a bandgap about 5 electron volts can operate at both very low temperature and very high temperature. It's also radiation resistant, and also it is optically transparent down to 250 nanometer, right? So this means that you can integrate a lot of display and imaging system onto that. So this means that the gallium oxide logic IC can be an excellent platform for highly integrated, compact, energy efficient, and robust electronics and photonics. And in addition, it's worth mentioning that the 12-inch gallium oxide substrate has also been developed, right? So 12-inch is the standard, the largest size of the silicon CMOS process. So if you can realize a very large substrate, it indicates that you can have a lot of room in terms of cost reduction. So the question for us is that, hey, what kind of architecture we would like our gallium oxide logic IC to have? Obviously, most of our electronics are based on unipolar CMOS. What is unipolar CMOS? It has one NMOS and one PMOS. You integrate them together, you form a CMOS IC. So unipolar CMOS, there's nothing wrong about that, right? But the problem is that once you get into very bleeding edge fabrication node, like 5 nanometer, 7 nanometer, 3 nanometer, the cost and complexity of fabricating two different transistors is significant. Because here you are not fabricating one transistor, you are fabricating two different transistors in a very dense manner on the same wafer. I can tell you that most of the student at house would not be able to fabricate two different devices on the same wafer in our clean room today, right? It's actually very complicated. For example, the cutting edge silicon CMOS will require over 70 steps of ion implantations, right? Which is very costly and complex. That will also reduce the yield as well. So our question is that, hey, if the unipolar, if we don't want to use unipolar because we don't want to fabricate two different kind of transistor, can we just fabricate one kind of transistor? The answer is yes, theoretically. So there is a transistor called ambipolar transistor. Obviously, right, that ambi represents two, right? Like amphibious and others. So ambipolar transistor can switch its polarity, based on the control voltage. And many simulations have predicted that this ambipolar transistor can cut down the cost, number of logic gates, delay, and energy consumption by 30 to 70%. Right? However, most of the ambipolar transistors developed previously by different companies like IBM and Samsung are all based on narrow bandgap materials. And as I mentioned earlier, narrow bandgap materials do not even survive in those extreme environments, including silicon. Right? So can we develop the first wide bandgap ambipolar transistor and CMOS? So yeah, so let's do it, right? So this is the fabrication process of our ambipolar transistor CMOS. And here is a video. Yep. So we start from silicon substrate with deposit gallium oxide, and then we pattern that, and then we deposit nickel oxide. So nickel oxide here is to provide holes because gallium oxide is primarily N-type material. And then we deposit hafnium oxide as a dielectric and the metal as a source drain and gate. And we flip it and we remove the silicon substrate and then put the dielectric and metal on the backside because we want to develop the so-called gate all around transistor, right? We want to have the gate around the channel so that we can have a better control. So by the time of the publication, I believe that we are the third organization after Intel and IMAC that reported the gate all around stack CMOS. So this is how it works, a little bit of physics. If you look at the right, when you have the gate voltage larger than 0, right, you have the move up of the Fermi level, which create the accumulation of electrons in the gallium oxide, but then depletion of the nickel oxide. So when your VG is larger than 0, you only have the electron current. But when your VG is smaller than 0, okay, you have the depletion in gallium oxide and then accumulation of holes in nickel oxide. So in this case, you output hole current. So by applying different bias, we can actually change whether the transistor is NMOS or PMOS. As I mentioned, what we want to use it is for extreme temperatures, right? So we actually measure the transistor anywhere from 25 degrees to 300 degrees Celsius. As you can see here, the transistor actually operates very stably at those temperatures. We didn't go even higher temperature because our probe station is limited at 300 degrees C. However, I believe that this transistor can operate at even higher temperature. Yeah, so based on this transistor, we demonstrate the first wide bandgap ambipolar CMOS. So those are, again, programmable transistors and ICs. And this is just a simple demonstration of the basic logic gates like the NOR and NAND. So lastly, I would like to talk about more. So how do we continue to increase the transistor density? So again, going back to the Moore's law, the transistor density increase has slowed down greatly. And one of the reasons is that in the past 6 decades, right, people have only focused on 2 axes, x-axis and y-axis. This means that the increase of the transistor density has largely is because like people are trying to make the transistor smaller and smaller. And all of our phones and computers and laptops today only have 1 stack of transistor in our chip, only 1 stack, right? So when you talk about 5 nanometer to 3, 3 to 2, 14 to 10, it's all about how can we make this 1 stack of transistor smaller so we can have a larger density. So obviously, as you know, there's another axis, which is the z-axis, right? So instead of focusing on scaling in x and y plane, can we actually scale in a z-axis? Meaning that can we stack layer of transistor on top to increase the transistor density? Obviously, we are not the only one who are thinking about that, right? If you look at some of those large corporations, Intel, Samsung, and TSMC, they are all trying to develop the 3D stack silicon CMOS transistors. However, their yield is very low, and it's very difficult for them to commercialize. If you look at the roadmap of those companies, they will not commercialize this stack transistor until 2040 plus, right? That's a long way from today. And the main reason is that the fabrication, the thermal budget of the fabrication of silicon is very high, meaning that you will need very high temperature to fabricate those stack transistors. So it is okay when you fabricate only 1 stack of transistor. But when you are fabricating the second floor, the very high temperature, the very high thermal budget can damage and destroy your first floor, right? This is not possible in building apartments as well. So for us is that, hey, if we go back to the ultra-wide bandgap semiconductor, can we pick some of them which may have low thermal budget and we put it into the soil of the oak tree so that we can grow the branch of the more? Yeah, the answer is possibly. Okay, so there is a wide bandgap semiconductor that we are working actively called indium oxide. It's a great candidate because it has a very low thermal budget. And also it can do very large scale wafer as well. It can go not just 300 millimeter, which is standard for silicon. It can go to meters and tens of meters, right? So it's not only it has low thermal budget, but also it has good scalability. Although the indium oxide may not be used for high performance computing like LLM training, it's actually a great candidate for edge applications. Like recently, Arm Holding and Pragmatic Semiconductors have published a paper and where they demonstrate the first flexible 32-bit Arm microprocessor, right? They actually use a system material called IGZO, I representing indium. However, there's a problem in this study. They only have 56,000 transistors over an area of 8 times 8 millimeter square, right? 8 times 8 millimeter square is a small area, but in today's state-of-the-art microprocessor, it can have billions of transistors. For example, the chips in our smartphone has a size about 10 by 10 millimeter square, and it has about 10 billion transistors, right? So like the reason is, there are two reasons for that. One is that they didn't use the bleeding edge fabrication node. They didn't use 3, 5, 7, 14 nanometer. They use 180 nanometer, right? So that is one limitation. Another limitation is that they only have one stack. They did not leverage the stackability of those wide bandgap semiconductors. So our goal is to develop highly stackable transistors so that we can effectively increase the transistor density. So what are the applications for those edge scenarios, right? So that include wearable healthcare and bioelectronics, high performance flexible display, including AR and VR, smart packaging and intelligent IoT, and 3D neuromorphic edge AI, and also space and defense electronics, because it require electronics that are highly conformable. So this is the process flow. Again, it's a short clip. We started from silicon substrate, okay, and then we have to refine and optimize the process where we have to deposit tens of layers of different semiconductor active and passive layer on top of each other. So that include the insulation layer, buffer, and the active layer, which is a 5 nanometer thick indium oxide channel transistor, and also metal as well for the source, drain, and gate. Yeah, on top of that, we have to use the dielectric as well. So in this study, we fabricated 10 stack of transistors. It's an entirely manual process, because obviously we have our nanofab here is for research, so it's a manual process. So it actually took my students 3 months to fabricate this 10 stack. And student came to me and asked me like, hey, do I have to fabricate more? I said it's enough. It's already a world record, by the way. And then therefore, like it's just to demonstrate that the idea that we can actually optimize the design and the processes to realize these highly stackable transistors from only one stack. So one of the key things, for the stack transistor is the interfacial roughness. Electrons are very demanding nanoparticles. They only want to run on a very smooth highway. It does not want to operate in bumpy road, right? So ideally, you want to have your interfacial roughness less than 5 nanometer, so that electron can move very efficiently without being scattered. So if you look at from stack 1 to stack 10, at stack 1 we have a roughness about 1 to 2 nanometers or so, right? Which is actually quite good. And if you start to move up, at stack number 10, we have a roughness about 2 nanometers, which is still quite acceptable. So I believe that like if we are going to continue to stack more transistor, we can actually shoot for an even larger number of stacks. Yeah. So as I mentioned earlier, most of the devices, most of the chip today only have one layer of transistor. So how do transistor talk to transistor? So they have to put copper wire to connect those transistors so that they can talk to each other. So it's actually more like a lateral interconnect, right? And those distances can be very large. As I mentioned, a normal chip have a dimension from about 10 by 10 millimeter to hundreds of millimeter, for example, like a high performance GPU. So the interconnect distance is actually can be in the range of micrometer to millimeter. For example, today, like if you input X amount of watt into a computing chips, it actually will consume more power in the interconnect rather than transistor switching, rather than the computing itself, right? So this is a significant drawback of only a single stack of transistor as well. So by actually stacking transistor on top of each other, we can realize something that the conventional chip cannot do, which is vertical interconnect. What is the distance between our transistor here? 50 nanometer, right? So the interconnect distance can reduce from micrometer to tens of nanometer. So you can actually reduce the amount of power consumed for electron to core another electron, for transistor to core another transistor. So in here, we can, for example, interconnect the transistor from stack 5, between stack 5 to stack 4, stack 6 to stack 2, basically the matrix. We can do any interconnect as we want. And then we demonstrate that these inverse inverters have pretty good gain, around 40 to 50, right? Which is actually comparable to the state of the art. So since this paper was published, because this was the first study where people managed to 3D stack many layers of transistor, it has received a lot of attention from the global community. Till today, it has been downloaded over 27,000 times. Okay, so despite that, we have made some good progress in the transistor stacking here. Here, we only use one material, which is indium oxide, which is an N-type material. So the IC here is actually NMOS. But as you know, NMOS actually can have a large static power loss. So what we want to do is that we want to move from highly stacked NMOS to highly stacked CMOS, because that will be the eventual technology for edge applications. So as I mentioned, the metal oxide typically are N-type, right? So we need to look for P-type material, which have a low thermal budget, but also is highly scalable. So here at KAUST, we have Professor Martin Heaney, who is an expert in synthesizing the P-type oxide transistors, right? As you know, because of the development of organic display, like the OLED display, the P-type semiconductor now is an organic semiconductor today is actually highly scalable and low cost. So we actually brought his materials into our stack, and then basically we stack our NMOS and PMOS one by one and realize this heterogeneous 3D stacking, or we call it hybrid CMOS. Yeah, and then this is again a characterization of the interfacial roughness. So when you have different type of semiconductor into the same stack, technically it becomes much more challenging, right? Because those different semiconductor will require different processes and so on. So if you look at the bottom, the stack number 1, we have about, the roughness is actually about 0.55 nanometer, right? So 0.55 is actually very small roughness, because each atom here, like the distance between atom and atom is about half of that, right? It's about 0.25 nanometer. So 0.5 nanometer is a very tiny roughness for electrons to move around. So we started from about less than 1 nanometer. And when we move up, you can see that the roughness started to move from less than 1 nanometer to 1+ nanometer, eventually to 3+ nanometer, right? So this indicates that, we still need to do a lot of work in terms of, optimizing the whole process, the fabrication process to reduce the interfacial roughness for the stacking. But nevertheless, we managed to stack 6 on the silicon substrate, right? Half NMOS and half PMOS. Yeah, so those are the characteristics of NMOS and PMOS. From each stack, we measure about 100 transistors, and then we conducted the statistic analysis. So from those statistics, we note that they actually have pretty tight distribution of different characteristics, including subthreshold swing, threshold voltage, on-off ratio, and so on and so forth. So based on that, we demonstrate the CMOS operation. Again, those are some basic logic gates, NOR and NAND, and because this is the first highly stacked 3D CMOS, it also has attracted a lot of attention globally. So far, since it was published about 6 months ago, it has been downloaded over 19,000 times. And also, we have noticed that media of many different countries have reported, including media in English, Chinese, Spanish, French, Russian, and so on. Okay, so in the last 20 minutes or so, I have talked about several works of my group that actually help the growth of different branches for this semiconductor oak tree. So what will be the future? What do we want to do in the coming years? So basically, I want to double down on those activities, right, to grow those branches. So let me, spend a few minutes to talk about my future plan. So I have 4 future plans directly derived from the research I just talked about, right? The first one is that we want to scale from micro LED to nano LED. Number 2 is that we want to go beyond gallium nitride. We want to have even larger bandgap semiconductor, which is aluminum nitride power devices. And for the extreme environment as well, we want to continue to grow the ecosystem of the gallium oxide IC, which we started. And number 4, we want to continue to develop the heterogeneous stacking to have the 3-dimensional system on a chip. Let's start from the nano LED, right? What I talk about the benefits of having micro LED. If you move the dimension from micro to nano, meaning dimension below 1,000 nanometer, which is 1 micrometer, you have even better different benefits compared to micro LED, including communication, display, and many others. So for our future work, we want to develop the wafer scale process based on lithography and also on wafer integration of nano LED and driver IC to have a very compact display and communication units. We also want to integrate the meta surface and nano LED as well. In my group, we have, those are the paper we published in the previous years. We have not only done a lot of work on the micro LEDs, but also we have done a lot of work on the meta optics as well. So meta optics is an immersion optics that you can steer the direction of the bin with a thickness of only hundreds of nanometer of active area, right? So, and this is like a preliminary nano LED fabricated by my student. It's a display of Panda. It has a pixel size of about 850 nanometer, right? So we are continuing to develop more of this technology for various applications. Number 2 is that we want to move beyond gallium nitride and silicon carbide, right? If you look at the figure on the bottom left, this is basically show the polygon figure merit for different power semiconductors. Obviously, first of all, we have silicon, and now it's moving to silicon carbide and gallium nitride. And the ultimate power semiconductor here is aluminum nitride. It will have the largest possible figure of merit. So in my group, we have done a lot of preliminary works related to aluminum nitride power transistor. For example, last year, we reported the first aluminum nitride MOSFET. Because as you know, most of the power transistor today are all MOSFET. Most of the CMOS are almost MOSFET because it's the most stable and scalable transistor technology. So by developing the first aluminum nitride MOSFET, we actually have a very solid foundation for future development. And also we have done work related to very low contact resistivity on the N-type aluminum nitride. And also we have demonstrated several state-of-the-art. For example, like the state-of-the-art aluminum nitride epitaxy on silicon by MOCVD, and also the aluminum gallium nitride and aluminum nitride SPD with high breakdown voltage. And number 3, we want to continue to double down on the gallium oxide integration IC that we started, globally. So I earlier talked about the first gallium oxide ambipolar CMOS that can operate up to 300 degrees Celsius. And recently we published a paper where we report the first cryogenic gallium oxide transistor as well. And that transistor IC can operate at about 2 Kelvin, which is already below the background temperature of the deep space, which is 2.7 Kelvin. And also in the last few years, we have developed different building blocks based on gallium oxide for gallium oxide IC, right? That include the first gallium oxide flash memory, the first gallium oxide bidirectional switch, the first monolithic gallium oxide gate driver IC, and then the first gallium oxide RTL inverter IC. So I think with those building blocks, we are going to continue to develop and improve the performance of those devices in IC so that we can have a highly compact system for various applications from space to quantum computers. And number 4, it's about the 3-dimensional large area system on a chip. Earlier, I mentioned that we have done works on the homogeneous stacking NMOS and heterogeneous stacking CMOS. What do we want to do in the future? This is what we want to do in the future. We want to integrate not just logic, right? We also want to integrate memory, power, RF, optoelectronics, or sensor into the same chip. So that system will have very broad application because it will be a very highly compact, efficient, and very high-speed system. Okay, so next I would like to have an acknowledgement. Obviously, I didn't do any of the work. Those works are mostly done by my students and postdoc. And also I'd like to acknowledge the support of collaborators here at KAUST, but also globally as well. And next, I would like to thank the funding support from KAUST and also external resources. And also my group has benefited tremendously from nanofabrication and imaging collab. And thank you, Ken, for coming today. And for the alumni, from my group, especially PhD students and postdoc, Many of them have become faculty members of different universities in the UK, United States, Taiwan, China. And also the other alumni of my PhD and postdoc have become either engineers, postdoc fellows, or and some of them have become consultants, so on and so forth. I'm very proud of their achievement, and hopefully they can contribute to CAUS in the future. So in summary, first of all, I talk about my experience here at CAUS, and then I discuss why the slowing of the Moore's law offer a historic opportunity for the ultra-wide bandgap semiconductors. And next, I use several examples to explain how my group has made contribution in those several branches, more than more, and beyond more. And lastly, I discuss my future research plan related to those areas. Yep. Finally, thank you very much for your attention, and thank you for this wonderful journey at CAUS. Oh, it's many steps. I know you are expert in a PVD. So yeah, we use a lot of PVD and also CVD process. So for each step, they will introduce a different issue in terms of having increase or decrease the roughness. Another one is the strain, right? So when you some of those layers are highly they have an order atomic arrangement. So when you place one layer of atoms on top of another atom, the atoms at the bottom will not be happy. It will either try to squeeze or expand your lattice, right? So all of those can actually increase or decrease the surface roughness. Oh yes, that has to be improved a lot. But also, in addition to that, the lithography has to be improved as well. So, but eventually, it's a hard work of student. I think I'm lucky to have a lot of good hardworking students. I think they are determined, to actually realize a good device and actually for different applications. Yeah, actually, thank you, Mohammed, for coming today. He's from the Research Translation Hub. He's working with me on a small TRG project. Also submitted one TRG as well. So the project we're working on is related to power electronics. Okay, so I think that's because right now, if you think about it, 90% of power electronics today are still based on silicon. Right? This is very similar to a few years ago when people say that 95% of the chip in data center are still CPUs. Okay, so there is a tremendous amount of potential to actually replace those silicon, whether in the room, in the electric vehicle, in the grid, in machinery, and so on. So I think, yeah, the power electronic is a low-hanging fruit, but then the other areas can also be quite interesting and promising as well. Thank you. No, I did talk about space. Yeah, correct. Uh, if you only have the devices, it will be a problem. However, you can combine the devices with algorithm to compensate the change. The problem with the silicon transistor and silicon electronics today is that it does not even work at those temperatures, right? Either very low or very high temperature. So as a result, you know it very well. You will need to have additional payload in order to support it, because you will have to provide the air conditioning system or the cooling system or the heating system, right? And also many silicon electronics today have to be shielded by heavy metal like lead as well, right? So those ultra-wide bandgap semiconductor, maybe later we can talk about some collaboration as well, is that it has a very large bandgap, right? So the reason it's the silicon can be easily disturbed by different temperature and radiation is that it has a very small band gap. So the band gap is the minimum amount of energy for electron to become disruptive. Okay, so for silicon is about 1.1 electron volt. So 1 electron volt is about 10 to the minus 19 joule, right? So it's a very small energy unit. But for those ultra wide bandgap semiconductor, the band gap is about 6 times of that, right? So so the probability of those semiconductor being disturbed by radiation or high temperature become way less. For example, I didn't talk about here today, but the highest temperature that my group has worked on for sensors based on aluminum nitride is 950 degrees Celsius. The lowest is 2 Kelvin. Yeah, so we have a wide range that we can tackle because low temperature can be an issue too. I happen to talk to one of the chief engineer in charge of the space rover system of China, right? So they sent the rover, I think last year, to the backside of the moon, right? Basically, they told me that the rover has to be shut down for half of the time. The reason is that if they want to operate it, because the sun only covers half of the time. So for the other half of the time, they don't have the energy. They can heat up the rover as well. However, that basically increase the payload. That will increase the risk of the lunar mission. So I think when we develop those cryogenic electronics and also high temperature electronics, it can work in both ends, right? So in the future, the lunar rovers can potentially operate all climate, so to speak, right? So that can definitely increase the amount of human exploration and different activities on those in those extreme environments. Yeah, thank you for the question. Oh yeah, I think the packaging as this so-called back-end process is actually very, very important. Yeah, I think this is something that I think potentially the university can think about investing, right? Because for example, like TSMC and others, they are actually putting a lot of, because it's very hard for them to reduce the size of transistor today. Every year, the transistor density only increased by about 10%. Previously, 40%, right? In the previous years. So now a lot of their efforts are focused on this backend, like packaging and others, 3D packaging, heterogeneous packaging, wafer bonding, and so on. So I think it will be great if we can have more capability of that. That will definitely help the commercialization as well, because we cannot just sell wafers and dies, right? We have to sell chips. So I think that is a very important resource to have. Yeah. Mm. Uh, yes and yeah. Thank you for the question. The answer is yes and no. Yes and no. Because commercially, people work on 12-inch wafers, right? Like or larger. And what we are working on is, for example, 2-inch or 4-inch. Okay. So there is a ramp up stage that people have to work on. Another one is that in industry, it's mostly automatic. Okay. So if you go to a state-of-the-art fab, you will see those wafer carriers moving high speed. They have their highway, But so I think that automatic process can be manually controlled as well. So the experience that we develop here can also be transferred in those fab, but it will take years, take some time to actually have a fully transfer. Just to give you like a high level kind of context. So typically, the transistor that we are using in our phone today was firstly developed in the lab 10 years ago, right? Was first developed, like, for example, the gate-all-around transistor we're using today was developed reported in university lab or company lab 10 years ago. So actually, it takes time to ramp up those things because the semiconductor manufacturing is is probably the most demanding manufacturing human has ever known, right? Basically, you have to cramp billions of transistors in millimeter square area. So you need to have very high yield. And also, every single transistor has to work, right? For example, if a few transistors on your chip do not work, then your phone may die or have malfunction, right? And so it actually takes time for any semiconductor technology to be commercialized. Yeah. So, but anyway, back to your question, it's fully transferable. There is a ramp up and then a transfer process. Thank you very much.